Hello. Thank you for taking the time to watch our presentation and learn about our project. We are a senior design team from San Diego State University, spring 2022. Our project is called Solar Trigeneration, and we spent the past 2 semesters researching, coding, and building a graphical user interface, or GUI, to analyze the energy usage data of a building. Any building with the proper measurements that meet our specifications, a cost and CO2 analysis can be realized. Some background information. We are sponsored by a company called Enersion. They are a clean energy startup from Canada known for their solar trigeneration system. The name comes from the purpose of their system, which takes in solar energy and hot water to power their chiller to specifically provide cooling, but also electricity and heating to their customers' building. Thank you to our advisor, Professor Saeed Manshadi, who is also the SDSU co-director for the Southern California Energy Innovation Network. With his guidance and support, we were able to design the GUI and produce the appropriate results. The main goal of this project was to help our sponsor Enersion determine the energy profile of any commercial building. Then, if their system was installed, we can calculate the energy savings and determine the total energy cost and CO2 emissions, such that a customer can understand how the installation of Enersion's trigeneration system can help the customer meet their decarbonization and other goals. Our GUI is a standalone data visualizer and can show the cooling, electrical, and heating profile of any building. These data points are converted into total energy usage measurements, estimated total cost in dollars, and the CO2 emission output in terms of metric tons of CO2 per hour. The main use case for our GUI is to see the benefit of installing Enersion's solar trigeneration system and compare its expected values to the current usage and demand of the building. In our case, we modeled our GUI after the measurements from sensors that were pre-installed in a building on our campus, the Engineering and Interdisciplinary Sciences, or EIS, building. With the raw data obtained from these sensors, we were able to calibrate our GUI and formulas for calculating the cost of energy upkeep, the CO2 emissions, and the effect the trigeneration has on the electrical, cooling, and hot water energy usage. These formulas are implemented using PV panel specifications, solar sizing considerations, solar availability for a zip code, and many other parameters. The presented software is not limited to the EIS building at SDSU. It can be applied to any building with cooling, hot water, and electricity data with at least 1 year of available data. The solar availability and temperature data will be gathered based on the zip code for the user. And a note, the raw data uploaded to the GUI must be formatted correctly. First, all files must be in hourly timestamps for a year, resulting in 8,760 data points. Next, the cooling usage profile values must be defined in CFM, and the hot water usage values must be defined in kBTU. Lastly, the electrical usage values must be defined in kilowatt hours.
This is the main face of the GUI. There are 3 panels, left, middle, and right. On the left-hand side in the middle, there are buttons to upload our input data files. Here the user will upload the building's cooling, heating, and electrical data files, followed by the CAISO total electric demand and CAISO total CO2 production. These files enable us to create a ratio between the CO2 production of the entire state of California and the CO2 production of just the building of interest by using the electrical energy usage of all of California and electrical energy usage of just the building of interest. The user can change these files to represent the CO2 production and electrical usage of the building of interest state or area. The light turns from red to green when it's been successfully uploaded. I will now demonstrate the file upload process. In the weather data section in the top left, a zip code can be specified along with a specific year. Once that is done, the Get Data button will be pressed that will initialize our API calls and obtain the weather data for the specified location. This is important so that the GUI may be used for any building in any location covered by the API. The light turns from red to green when it's been successfully retrieved. I'll now demonstrate the weather data retrieval process. The time of use rates can be adjusted in the lower left side panel. The initial rates seen here were chosen to match the commercial rates of the local utility provider. These rates change based off of time of use and are categorized into on-peak, off-peak, and super off-peak, and separated by summer and winter rates. Natural gas rates are a constant value given by the utility and can be adjusted here as well. Following any adjustments, the build button must be pressed. Next, the user will specify how many panels their system will contain and adjust the sizing of panels if required by Enersion in the solar panel parameters section. The number of panels will correspond to how much roof space is available. The size of the panels is currently provided by Enersion as 1.96 meters squared and is the value that is initialized in the GUI. Thermal rating is the amount of heat that can be captured by a solar panel. Power rating is the amount of energy that can be captured by the panel. Thermal COP is the efficiency of the compressor system used by Enersion to convert the hot water to cooling. These values are given as 0.7, 0.35, and 0.5 respectively, and have been initialized in the GUI. At this point, all data will have been entered into the GUI, and the user will now be able to view the yearly data that they entered along with the calculated data based on the sizing of the Enersion system. The first tab is the temperature tab, which shows the hourly temperature and temperature trend throughout the year. At this point, all data will have been entered into the GUI, and the user will now be able to view the yearly data they entered along with the calculated data based on the sizing of the Enersion system. The first tab is the temperature tab, which shows the hourly temperature and the temperature trend throughout the year. The second tab is the solar radiation tab, which shows the hourly solar radiation and the solar radiation trend throughout the year. The third tab is the electrical usage tab, which displays the electrical energy usage with and without the installation of trigeneration and the resulting trend lines of those hourly electrical energy usage graphs. The fourth tab is the cooling demand tab, which displays the cooling demand of the building with and without the installation of trigeneration and the resulting trend lines of those hourly cooling demand graphs. The fifth tab is the hot water usage tab, which displays the hot water usage of the building with and without the installation of trigeneration and the resulting trend lines of those hourly hot water usage graphs. The sixth tab is the cost tab, which contains the energy upkeep cost graphs with and without the installation of trigeneration, as well as the cost trend lines for both the hourly energy upkeep graphs. The seventh and final tab is the CO2 emissions tab, which shows the CO2 emissions of a building with and without the installation of trigeneration, as well as the resulting trend lines from the hourly CO2 emissions graphs. The date range box in the bottom left allows the user to specify a range of calendar dates to view the data from. For example, the user can select the interval from January 20th to February 20th to see 1 month, or October 1st to October 8th to see 1 week of fall. Or for instance, see just summer by selecting June 21st to September 22nd. Or even just April 14th to see the data for 1 day. Next, the interval selector changes the averaging of the data that is being viewed. Options for the interval are hourly, 8-hourly, daily, lastly, monthly. These work for any period of time and additionally adjust the values on the right side panel. Lastly, the monthly interval selection shows the entire year rather than the selected date range, since the understanding of the entire graph is simple as there are only 12 data points per dataset. Next, to ensure that the presented software is applicable to any utility rate tariff, we made sure the user could easily adjust their rates with sliders to account for potential increases in rates. There are two sliding scales on the lower section of the GUI that can adjust the electrical and gas rates. If we increase the electrical rate or increase the gas rate, the cost graph and cost output on the side panel will adjust accordingly with the specified cost multiplier. Note how increasing the electrical slider by 2 times causes the cost of energy upkeep to increase almost 2 times. While decreasing it to 0.5 will cause the cost of energy upkeep to decrease by a factor of 4 from the previous value. These values aren't exactly double or half because the cost of natural gas is separate from the electrical rates. The natural gas rate slider works in the same way. Next, on the right-hand side is a panel with several values. These overall values are calculated within the GUI using its integrated formulas. Their output is shown in the upper right. Selected periods, electricity, cooling, and heating, with and without tri-generation system. Total selected periods, cost and CO2 produced are also shown. The actual cost and CO2 savings for 1 year are $31,097, and CO2 savings are 51,469 metric tons, respectively. For monthly calculation, monthly calculation in January comes out to a total of $1,586 saved and 2,690 metric tons of CO2 saved. Lastly, for daily value, January 1st, $56 is saved and 64.8 metric tons of CO2 are saved. The third section shows the difference numerically with and without tri-generation for the selected period. Switch back to this and I'll cut this out. Over the course of student design, we have learned a lot about working together as a team for a common goal. Using the skills we developed through several years of engineering curriculum, we successfully completed our GUI. It has all the necessary functionality to be useful to users who wish to comprehend the energy usage data of their building. After using this tool, the user will be able to see exactly how much a building could save with the installation of Enersion's tri-generation system. This is important because it provides companies looking to retrofit their old buildings an easy way to understand the cost and CO2 savings from the installation of tri-generation. Going forward, this GUI can be flexibly used in numerous applications if handled appropriately. Thank you for watching.